Well, let's see how you're going on this. So the room is 18 by 24, 8-foot high walls. To find the wall area, the easiest way is to just unfold all the walls to make one big long wall. Still going to be 8 feet tall. We've got 8 feet, 18 feet, 24 feet, another 18 feet, and another 24 feet. Obviously, I'm not drawing the scale here. We could find the area of each piece individually if we wanted to. 8 times 18, 8 times 24, and add them all up there. Or we could treat it as one big rectangle. What's the length of this all the way across here? 84 feet, good. So 84 feet would be the length of that big rectangle. That's nothing more than the perimeter of the room. When we are finding surface area or wall area, the perimeter of the room, using the perimeter of the room times the height of the wall, is one of the strategies that's done to find that wall area. So we have the perimeter of 84 feet. The wall area is just going to be that 84 feet times what? 8, which gives us 672 square feet. You guys know the wall area of your shack over there? Not a clue. You know the dimensions. Figure it out. Assume that the fourth wall is a complete wall, not just an opening, by the way. It is a full 8 feet tall. It is a full 8 feet tall. 7 feet tall. Okay, that sounds about right. What are the dimensions? It's 8 by 12. So yeah, that means the perimeter of the base is how big? 40. And so yes, 40 times 7, 280 square feet. Not so bad. It's a lot easier to do wall area if you have that shortcut. I see so many people go through and they figure out wall by wall. It's just a lot of extra work. So here we have a room that is 6 feet, 6 inches wide, and 8 feet, 4 inches long. Find the wall area. The wall height is 7'8". So first thing you have to do is find the perimeter. What'd you get for the perimeter here? 27'8" sound right to everybody? So 27'8". So now we have to multiply that by 7'8". Now, if you remember when we were talking about multiplying measurements, so we don't like to multiply with dual measurements. So we have to express these, since we want it in square feet, we have to express these in all feet. So 27'8", how would we express that all as feet? Well, 27 isn't going to change. How do we turn 8 inches into feet? It's by 12, yes, 8/12, or 2/3 if you want to reduce it to that. So that's 27 2/3 feet. 7'8". So same thing, 7 2/3 feet. So then we need to multiply that. I get 212.11 square feet. Does that look right? That one wasn't very nice. Okay, so you guys have a couple of quizzes for me, actually. One is the quiz 9-28. What are the dimensions on the side of the triangle? Okay. So since we don't have any right angles here, we have to use that hero's formula. So you have to find the perimeter. So we add those all up. What do we get for the perimeter? 26 inches. Okay, what's next? Divide by 2 gives the semi-perimeter, which will be 13. So the area then will, yes, will be the square root of perfect. So that's the square root of 13 times 2 times 5 times 6. Get her? Okay. Perfect. Then you said number 2? Number 2 is the little wedge of the circle, the sector. What's the angle on that, 84? And what was the radius? 12 centimeters, okay. So to find the area of a sector, we start out finding the area of the whole circle. How do I find the area of that circle? Well, 3.14 times 12 squared, okay, which is? You went one step. 452.16 centimeters squared. So that would be the area of the whole circle. So how do we find the area of just that sector then? It's not a full quarter circle, so we can't just divide by 4. The fraction of the circle, remember, is that central angle, the 84 degrees, over, what's a full circle? 360. Any other questions? Okay, so if you have any others to finish up, just get those turned in to me sometime before you leave here today. Thank you. Perfect. Thanks. Okay. Oh, sure. Yeah, and it'll sometimes give you the answers in terms of pi or whatever. Okay, so today we're going to look at, I promised you would keep looking at some of these composite shapes a little bit because it's something that people do struggle with. So we're going to look at something like this. We have a circular piece of lawn, and we are going to put a circular fountain in the middle and a patio around it. So this fountain is going to be 12 feet across. The whole piece of lawn is 40 feet across. So what we want to know is, what's the square footage of patio that's going to be put in there to fill in around that fountain? Well, there are actually 2 different ways to approach this, but one of the ways is way simpler than the other. And the simplest way to approach it is what we've discussed about finding a big area and subtracting out a piece that's missing. So here we would start by finding the area of that big circle. How would we find the area of that big circle? Not 80, but 20. There we go. Yeah, 40 is the diameter, so if you half of 40, it would be 20-foot radius. So what's that give us? So 1,256 square feet. And then what do we have to subtract out? The 12-foot fountain. So how do we find that area? Perfect. So what's that give us? We subtract to give us a total of Perfect. 1,142.96 square feet. Are the buses coming in, or? So this is kind of a classic problem. We're looking here at basically like a track. We want to find the surface of that track. There are actually a couple of different ways to break this up. How we break up the rectangles really doesn't matter. It's about the same difficulty either way. But it does result in we have, I'll probably cut more like here. We have the ends that are half circles, and then we have the straight parts that are just rectangles. How do I find the area of this rectangle? Ten times 80. Didn't need to hear for the rest of the day. What's that come out to be? 800 square feet. And of course, this one down here is going to be the same size. Actually, I think on a blind corner like that, he's required to honk his horn before he goes out anyway. On a blind corner like that, I think they're required to honk their horn. So a total of 1,600 so far, yep. Now for those end pieces. You know, we've talked about it's very useful to be able to cut things apart, but then to be able to put them back together to simplify how it is to find their areas. If I take these pieces here that we cut off at the ends and just put them back, what's that? Well, careful. It's still just going to be 60 feet across, right? Not 60 squared, but 30 squared. Which gives us what for that big area? Pardon me? 2,826 square feet. So now that's the big circle, but of course there's a little circle missing out of the middle here. What's the radius of that little circle? Yeah, if this is 10 feet here, if it was 30 out, it's going to be 20 now, right? No, it won't quite work. So it'll be pi times 20 squared now to get us that small circle. So that come out to be 1256. So then we subtract the 2826 minus the 1256 gives us what? 1570. So that, of course, has to get added to the 1,600 square feet we had before, giving us a total of perfect 3,170 square feet of area of that track to resurface. Oh, it's loads of fun. Okay, enough of that one. So the next step for us is to start talking about volumes. Now, when we talked about areas, we talked about the idea that all areas are based on a rectangle. And that all areas are found by multiplying two perpendicular dimensions. When we look at volumes, it's very important that we put behind a lot of the formulas that we've memorized and look at the concept for it to make a lot of sense. A volume is an area taken one more step. So picture we have a rectangle sitting on the surface. Now I realize that looks kind of squished, but imagine we're looking at it from up above and kind of off at an angle. Let's say that's an 8-inch by 14-inch rectangle. To create a volume, we're going to take that area and we're basically going to lift it, pull it through space. And the air that it displaces, the space that it travels through, becomes the solid object that we're going to find the volume of. So we're basically just lifting it straight up. Like that. So the size, of course, this forms a box, which is the most basic volume we can find. The size of that box depends on two things. The area of that original rectangle. We're going to refer to that original rectangle as the base. So it's the area of that base times the height. The height is just the difference between where the base was when it started, which was down here, and where it was when it stopped. We lifted it all the way up to here. So if that height, say, is 10 feet, this volume then is simply, well, the area of the base Oops, I shouldn't say 10 feet. I should have said 10 inches, not feet, to make it a little more. See, that height is 10 inches. Make it not mixed units here. The area of our base then is that 10 inches times 14 inches, which is how much? (112 square inches). So then the volume is the area of that base times the height. So it'll be the 112 square inches of base times that height of 10 inches, which gives us 1,120. Now, square inches times inches is inches cubed. Now, many of you already know that the volume of a box is length times width times height. You've seen that formula several times. So why do I try to redefine this new formula of area of a base times a height? Well, because too many of our shapes are not just boxes. Yeah, they're not just squares. Of course, our cylinder. Now, we've talked about these before. If this is eight feet across, 10 feet high. Now remember, the base is the shape that the whole solid object is created from. If I were to take the bottom of this and kind of lift it up, it would slide through the whole object. So the circle at the bottom is the base. Of course, the top is also that base. So the area of the base is there we go. 5 times 4 squared, or 50.24 square feet. Good. So the volume will be the area of that base times the height of 10. (502.4 cubic feet). I can't stress that enough, that being able to break it down like this rather than memorizing formulas saves you a lot of work, either memorizing the formulas or looking up the formulas when they come about. Now, on both of the shapes we've done so far, the base was the bottom. On a box, actually, any side could be the base. We typically use the bottom. But the base doesn't have to be at the bottom. For this shape, the base is this triangle here. Because if I take that triangle and slide it through, it ends up sliding through the whole object. It ends up matching up at the other end. So how do I find the area of that base? Five times 12 divided by 2, good. Which gives us 30 inches squared, good. What's the height here? Well, careful, not the height of the triangle, but the height of the whole figure. 20, it's the distance from where the base starts to where it ends. That's 20 inches. So to find the volume, it's the area of that base, the 30 square inches, times that height of 20 inches, which is perfect, 600 cubic inches. The nice thing about this formula is it doesn't even have to be a regular shape for the base. As long as it's a shape that we can break down, that's just to show that's the center of a circle. Pretend those look sort of round. So here, our base is this weird shape on the end here. To find its area, we'll draw it off to the side over here. It's simply a rectangle with a half circle on each end. What are the dimensions of the rectangle? 15 by 8. It's 15, not 18. Which gives us what for an area? 120 square inches. Then we have the half circles on each end. Which, again, we cut them off and we put them together to make one full circle. How do we find its area? Pi times 4 squared, which is 50.24. So that adds up to be the area of a base, which is 170.24 square inches. So even though it was an irregular base, we can still cut it apart like we have any other areas to find its size. Now, how do we find the volume from there? Yeah, we multiply that area of the base, 170.24 square inches times that height of 20 inches. 3,404.8 cubic inches. Not so bad? Easier than memorizing formulas? Good. A concept that works along with volume is density. Density is the amount of matter in a unit of volume. The way we measure the amount of matter is called the mass. A common expression of density, for example, wood has a density depending on the species anywhere from 29 to about 65 pounds per cubic foot. Pine is somewhere in the high 40s, depending on how dry it is. So let's say we're using wood that is at a density of 48 pounds per cubic foot. If we have material that if we have an object that we know has a volume of 4.2 cubic feet, we can now find the weight of that object. Now we look at this and I wonder, well, do we multiply? Do we divide? How do we know? Well, we use the units to tell us. We're starting at 4.2 cubic foot as our volume. The density, 48 pounds per cubic foot. We want to get rid of cubic feet and turn into pounds. 48 pounds per cubic foot is saying 48 pounds is equivalent to 1 cubic foot. So 1 cubic foot and 48 pounds. So the cubic feet are going to cancel out just like they would in any other measurement conversion. What's 4.2 times 48 pounds? $201.6 pounds. So that object, if it contains 4.2 cubic feet of wood, is going to be 201.6 pounds. Now you might be looking at this wondering, well, why did we go through 48 pounds equals 1 cubic foot? Anything that can be expressed as a rate like this can be used as a measurement equivalency. For example, let's say you're driving and you're going 60 miles per hour. That 60 miles per hour can be used as an equivalency. At that moment in time, for that vehicle, 60 miles is equivalent to 1 hour of travel. So if you're looking at how far can we go in 3 hours, we can take our 3 hours, put it over 1. We want to get rid of hours, we're going to put hours on bottom, miles on top. 60 miles is 1 hour. The hours cancel out. 3 times 60 is 180 miles. That one's the obvious application of just multiplying it out. But what if we were going a different direction? What if we wanted to know how long will it take to go 300 miles? To figure this one out, I want to get rid of the miles, so I'll put miles on bottom. 60 miles still equals 1 hour. So the miles cancel out. Now I've got 300 times 1 hour is 300 hours. 1 times 60 is 60. 300 hours divided by 60 is 5 hours. So it's that dimensional analysis, that measurement conversions that we've been using for all of our measurements. Actually is a very powerful tool. We don't have to memorize the formulas of, excuse me, distance divided by speed gives you the time, or time times speed gives you the distance. We can use the units to help us figure out what that calculation needs to be. Okay, it's close enough to break time. Go ahead and take our 10-minute break. Okay, so I want you guys to try some basic volumes in your notes here. So we're going to try the volume of a cylinder here. We're going to give you 12 feet across the base and 18 feet of height. I'll give you a couple minutes to work on that, then we'll go over it. So like any other volume, we start out by finding the base and the area of the base. What's the base of this shape going to be? Pi times 6 squared, good. And what's that give us for an area? 113.04 square feet. So then to find the volume, what do we do? 113.04 square feet times 18 feet. What's that give us? 2034.72. That's cubic feet. Any questions on that? So let's take a look at this one that's 16 inches. Seven inches, 11 inches, and 13 inches. Find the volume of that shape. So this one's a little trickier. So the base of this is this triangle that's at the bottom and at the top. How do we find the area of that triangle? If it were a right triangle, that would work. We have to use Hero's formula. If you double check that, 7 squared plus 11 squared does not add up to 16 squared. So that's not a right triangle. So we can't use base times height divided by 2. So yes, we have to use Hero's formula. So the perimeter of that is how much? 34. Yeah, 7 plus 11 plus 16 gives us 34 inches. So that means the semi-perimeter is 17. So the area is the square root of 17 times 17 minus 16 times 17 minus 11 times 17 minus 7, or the square root of 17 times 1 times 6 times 10, which is how much? 31 point what? 93. That'll be square inches. So from there we can find the volume. The 31.93 square inches times what? The 13 inches of height between the bases. Which gives us 415.18, okay, inches cubed. Well, how many cubic feet is that? You recall we talked about converting square inches to square feet and how the conversion factors changed. You just divide it by 12? Yeah. It's not inches and feet though, it's cubic inches to cubic feet. If you recall when we were looking at, if we had 3,456 square inches, and I turned it into, excuse me, square feet. What was my conversion factor between square inches and square feet? There we go, 144 square inches in 1 square foot. So this was 3,456 square feet over 144. So 3,456 divided by 144 gives us 24. So it's 24 square feet. Where did that 144 square inches in a square foot come from? Do you guys remember? It's just 12 squared. 1 square foot is 1 foot by 1 foot. It's less than 1 square foot. So it'd be 0.98 whatever square feet. Yeah, so 1 foot by 1 foot is 12 inches by 12 inches. 1 square foot is 12 by 12, or 144 square inches. So for cubic feet, one cubic foot is, of course, 1 foot by 1 foot by 1 foot. Of course, each of those feet is still 12 inches. What is 12 inches by 12 inches by 12 inches? 1,728 inches cubed. So 1 cubic foot is 1,728 cubic inches. So now back to our original question, we had 415.18 cubic inches. No, it is going to be way less than a cubic foot. That is true. So if we put cubic inches here going to cubic feet, 1 cubic foot is, what's the number? 1728, perfect. So the cubic inches cancel out, 415.18. Oops. Said 0.2406. We'll round it at that. Cubic feet. So it's less than a quarter of a cubic foot. .2402, okay. Okay. So 0.2403. So just like with our square units, we have to be very careful with the cube units to make sure we've adjusted our conversion factors to fit. One that I used a lot because I did a lot of concrete work was this one. .567 cubic feet going into cubic yards. Well, to figure out what our conversion factor has to be here, we're getting rid of the cubic feet. We'll put them on bottom. Going to cubic yards. Which is the bigger unit, a yard or a foot? Yards. So we're going to put 1 with the yards. How many feet are in a yard? 3. So this is cubic. So it's going to be 3 by 3 by 3. 3 times 3 times 3 is 27. There we go. So there are 27 cubic feet in a cubic yard. So the cubic feet will cancel out. 567 times 1 cubic yard is 567 cubic yards over 1. That's 27. What's that divide out to be? 21? So that's 21 cubic yards. I use that type of a conversion a lot. Let's say I am doing a basement floor. And let's say the dimensions on the inside of the wall, to keep it simple, are 32 feet by 44 feet. What is the area of that basement floor? (1,408) square feet. Now, if that is 4 inches thick, I can actually think of this as this 1408 as being the area of a base. And the rest of the solid is just a height of 4 inches. What's that? Wouldn't add 16 to it. What we would do is we would take that 1408 and we would multiply it because that's the area of a base, just like the bottom of the box. The height of the box is only going to be the 4 inches. But the 4 inches is in a different unit. So we have to convert the 4 inches into feet just by putting it over 12, 4/12 of a foot. So 1408 times 4 divided by 12 is 469 cubic feet. That sounds about right. So we have 469 cubic feet. So that's the volume of the concrete for that basement floor. Another reason why I do that area of the base times the height. It's pretty simple to do it that way. Let's convert that into cubic yards. What's the conversion factor? 27 cubic feet in a cubic yard, correct. So those cubic feet cancel out. 0.38. So yes, the 469 divided by 27 is 17.38 cubic yards. So let's say we're looking at a footing for the wall of a house. And let's say the outside dimensions of the footing here are 45 feet by 37 feet. The inside dimensions would go 41 feet by 33 feet. And we'll say the footing thickness is 9 inches thick. That's going to come into play in a little bit. First of all, code, we've talked a little bit about code for footings. The width of the footing must be at least twice the thickness of the wall. If you're doing block, of course, you're looking at a 10 or a 12-inch wall. That's why I made these 2 inches wide, or 2 feet wide. The thickness of the footing must be at least 1 inch of thickness for every foot of height of the wall, depending on soil type. So this is going to be slightly more than an 8-foot wall, so it has to be a 9-inch thickness on the footing. Typically, they try to do your basement walls. If they're poured, obviously they're stuck at 8 feet. It's more and more common now if they're doing a block wall to do an extra tier of block to give you that clearance, because when you do your basement floor, so there's your footing and there's your block wall sitting on top of the footing. When they pour the basement floor, they like to come up over the top of the footing a little bit so that it's continuous floor all the way out to the wall rather than pouring it right to the inside edge of the footing. There's a couple of reasons for that. One, it looks nicer on the inside. It is definitely a cracking point. Even if you do it like this, it's a cracking point because this is still only going to be 1.5 inches or 2 inches thick. The other thing is if you just stop right there, it's a water infiltration point. If you have any sort of negative pressure on water, it can seep up through that crack into your basement. So having the floor sealed tight all the way over to the wall helps avoid some of that. In fact, you mentioned the cracking point. It's become more and more common to run the slab all the way up over the top and fill in with sand to the top of the footing so that you avoid the cracking point. And if you're in an area where it is more known to have water issues, they use, it's kind of weird, it's kind of like a cross between rubber and putty. Comes in a big roll, it's called water stop. You plaster that up against the wall, and then you pour the concrete up against it. It sticks to the concrete almost like putty does, temporarily. It won't stay there for more than a day or two, but you pour the concrete up against it and it locks that into place. That way, if any water, oops, don't know what happened there. If any water ever starts to seep up through, it hits that water stop, and that water stop swells up like a sponge. And it swells up and fills any gaps so the water can't get through. The water stop is designed to have minimal pressure, so it can fill any air gaps enough to stop the water from flowing through, but it's not supposed to be enough to damage the concrete. Okay.
But sometimes the wall's like, it's not all like flat. So when the sand, you have the sand on the top, and then you go down probably an inch.
Sure.
For that.
Oh, for the footing?
Yeah, footing.
Yeah.
Waves sometimes.
Well, a lot of people, when they do you're looking at a block wall, or was it a poured wall? A lot of people, when they do poured walls, get really sloppy with their footings because they know that if you're dealing with your standard wall forms, they will even themselves out. When you lock them into place, they will, if there's a low spot in the footing, when you put the brace 2x4s on, it'll actually help lift those forms up into place. So if you ever look at them when they're set, some of them have gaps underneath the forms like that in spots because the footing was poured. I mean, they get the forms set decent, and then you just slop the concrete in there at the end of the day.
Yeah. You don't have to pretty much smooth it out. You just, when we did footings, they're probably 16 inches wide or so.
Sure.
And then it's like a 12 board.
Yep.
A 12-inch board. And you just have something where you just drag it all the way across, and they
Yep.
have the pump truck.
Yep. If I used a pump truck, a lot of times all I would use is a 3-foot landscape rake and just strike off on the top of my footings. I didn't even go back and trowel them. Well, yeah. Then of course you had to go back and lay in the L's for your wall rod. I have done a couple where it was the end of the day and we were in a hurry. So we ran posts and ran wires down through so that we could set the rod and tie the rod to the wire to hold it up. It all depends on your jurisdiction, your building inspector. Most building inspectors require at least 12 inches sticking up out of the footing, but we've had some that required 3 feet coming out of the footing. And that's tough to get those to stand up. Oh, sure.
When you're like 3 foot tall, and just, unless if you have them just perfect, something like that, sway one way or the other.
Yep.
I think good, aren't they though? So you can tie rebar over for the wall.
Yes. Yeah, that's what they're for. I have had a couple of building inspectors who made me want to scream, but required those verticals to be tied into the continuous rods for the footing. And that's a real pain because now you've got to have them, to tie them in, you've got to have them in before you pour the concrete. So now you've got to pour concrete around them and try to strike it off, and that's a real pain to do. I mean, I can see where it's better because the tying them in, they're held in place and they're not going to go anywhere that way. But it's a lot more work to pour the concrete then. Okay, so anyway, let's find the area of the surface of this footing here. So all we're going to do is find the area of the big rectangle. How do we find that area? Perfect. 37 times 45. What's that come out to be? 1,665 square feet. And then we have to subtract out the small rectangle. How do we find that area? 33 times 41, which gives us 1,353. We subtract to get a difference of 312 square feet. That is the area of the base. Now we know the thickness of the footing is 9 inches. How do we find the volume? We could. It'd be easier to convert the inches into feet. Yes, do 9/12. So what's that come out to be? What is it? 234 cubic feet. That's right, 234 cubic feet of volume is the volume of that footing. Now let's convert it into cubic yards. What's our conversion for cubic yards? Divided by 27, that's correct. 8.67 cubic yards. What do you think? Not so bad? Tell you what, since I didn't give you any work time on the quiz, rather than give you work time now and make you stick around on a beautiful day, as long as you promise to work on it at some point before next Friday, or to have it done by next Friday, we'll let you out of here. 7 degrees in November, I'm not gonna make you sit here on a Friday afternoon.